This video is part 2 of a discussion of single replacement reactions. I want to focus on metal and acid and metal and water reactions specifically now. The metal and acid reactions are pretty straightforward because the activity series doesn't lie, right? We've got hydrogen here. Anything above it will replace the H in acids. And if you look here, it says react with simple acids to form hydrogen gas. So these things will replace hydrogen in an acid. Metals and water are a little more confusing, and it's even more confusing if you consider when and how they happen. And I think that for us to start this discussion, we have to go back a bit to the idea of us having 5 basic types of chemical reactions, which is actually 6, which is actually 2. All right, and that's a joke I have, because what we really have for our types of chemical reactions, we have double replacement reactions, and we have redox reactions. And I'll write oxidation-reduction reactions. And those are redox. And the basis of a redox reaction is some transfer of electrons. And I've got a totally different set of videos that deal with oxidation-reduction reactions. But just in case no one cares about those, let's take a look here and say, the basis of oxidation-reduction reactions is a transfer of electrons. Specifically, you've got something that is gaining electrons and something that is losing electrons. And I'm going to change those words ever so slightly. We have some species that uses electrons and it is reduced since the electrons are negative. And we have some other species that produces electrons, right? And it is oxidized. So reduction is a decrease in oxidation state, oxidation is an increase in oxidation state, and that's what the basis of everything that's not double replacement, at least of our 5 simple reaction types, which are now 2, is based on. The overshadowing idea, I guess, with redox and how they relate to these 2 reactions is the idea of what is present and what can it do, all right? So I want to put these 2 questions in the forefront. What is present for the reaction? And a sub-question, what can it do? All right. And let's take a look at a metal-acid reaction, and it doesn't really matter which one. And it follows the activity series exactly as we would expect. We'll say we have something like maybe zinc and hydrochloric acid. We look at them and it's like, oh, that looks like a single replacement reaction. I've got something by itself and something in a compound. Zinc we're expecting to be a 2+, hydrogen a 1+, chlorine a 1-. We're not going to compare the 1 and the 1, we're going to compare the plus and the plus. And then we check our activity series. In order for the reaction to take place, the thing that's by itself, which is the zinc, must be above the corresponding sign, the hydrogen, in the compound. So here's hydrogen down here at the bottom. Here's zinc up here at the top. The thing that is by itself, the zinc, is above the hydrogen, so we expect the reaction to take place. These are going to switch places. We're going to get our new compound, which has zinc and chlorine. Don't forget, right? A 1 here doesn't mean a 1 here. That's what chlorine did with hydrogen. Now we're dealing with what chlorine does with zinc. Zinc's a 2+, chlorine's a 1-, so we'll need a 2 right there. And the other thing we have is hydrogen gas. The activity series actually says that in words. It says all this stuff reacts with simple acids to form hydrogen gas. So this has happened exactly as we would predict based on the activity series. And let's throw some balancing in there while we're at it, since I'm militant about that. We've got zinc, hydrogen, and chlorine. 1, 1, 1 on the product side, 1, 2, 2, and so we can fix that by putting 2 there. All right, it's balanced. So what I'm going to do right now is write next to this, I guess, what we have in this reaction, okay? Think of this in the bigger picture like a double replacement reaction. Let's throw some phases in here, like the zinc's a solid, the hydrochloric acid would be aqueous, the zinc chloride would be aqueous, and then the hydrogen would be a gas. And aqueous species, aqueous electrolytes, at least strong ones, don't exist as you see them, right? They dissociate. So zinc isn't part of the solution, it is zinc as we see it. And we have 2 hydrogen ions, and those are aqueous, and 2 chloride ions, and those are aqueous. What we're going for here is identifying spectators so we can look at the reaction that's actually happening based on what we see on the electromotive series, all right? On the other side, we have zinc ions and 2 chloride ions in our hydrogen gas. So the first thing I want to point out is I've got this chloride on both sides. It's a spectator. I'm not worried about it. And if we look at our definition of a spectator ion, something that remains unchanged on both sides of the reaction. In this case, it's there to balance charge. And that leaves the other things, right? We have a metal and hydrogen ions, and that is what I'm talking about right there. And I think this is one of the most important things you can drag out of this lesson is this little bit of information here. This reaction is actually a reaction between zinc and hydrogen ions. And if you look here, if you have zinc and if you have hydrogen ions, you can compare them. And I know I'm pointing at solid zinc, elemental zinc, and hydrogen ions when I do this, but that's intentional because I have solid zinc and I have hydrogen ions, all right? So I feel like I need to point at that or something, but I have zinc, Zn, like that, and it is right here. I have hydrogen ions, which are right there, and that's what we're going to compare. All right. We can look at this numerically, quantitatively, by looking at the half reactions. We don't necessarily need to, all right? My idea is what's present? Zinc is present. What's present? Hydrogen ions are present. What can zinc do? Zinc can oxidize to zinc 2+. What can hydrogen ions do? Hydrogen ions can reduce to H2. So I'm going to leave that on pause as we write the next reaction, and that's going to be one for a metal and water. I'm not going to choose zinc in this case, although zinc does react with steam. Let's just jump back to maybe something like calcium, which is going to react with cold water. So we'll say we have calcium and water. Now, the part that I think is super confusing is where it makes a metal hydroxide and hydrogen gas. So let's write out what our metal hydroxide would be and the hydrogen gas, and then we'll take a step back and see what's really going on. So in this case, we're going to have calcium, which is a 2+, and hydroxide. And if you're saying, well, how do I know it's a hydroxide? Well, number one, that's what we said right there, and that's how we know for now. Number two, that's the whole point. 1 minus 2 there, plus our hydrogen is by itself as a gas. I guess we should say this would probably be solid, but whatever. I'll declare that it's aqueous. It's a gas. And let's balance it. We've got calcium, hydrogen, and hydroxide. 1, 1, 1. And calcium, hydrogen, and hydroxide. 1, 2, 2. We can put a 2 there and balance the whole thing. So what do we have here in relation to what we have here? Well, let's look. I have calcium and I have water, okay? This is a liquid. In fact, I would like to put that in some glaring way so you can't miss it. H2O is a liquid, right? In this one, we had hydrogen ions, right? That's what we had. In this one, I don't have hydrogen ions. I have water, right? And if you look here, water is not on this activity series, just words for water. So that is the fundamental difference. The difference between this and this is that when I have a metal and an acid, I'm dealing with some metal and hydrogen ions, okay? When I have a metal and water, I'm dealing with some metal and water, and they don't show that on this activity series. So what I like to do, and then we'll go and take a look at where this water comes into play, but what I tell my students to do, to cut this corner, is to say, if you see a single replacement reaction with water, write the water as HOH, all right? So I would say write calcium, solid, plus 2HOH, right? And that's a liquid. It's going to give us calcium hydroxide still, 2 of those. It's aqueous. and hydrogen gas, right? It's balanced the exact same way, so I'm not going to go back through the balancing process, but what this allows us to do is say, oh, I'm just going to replace one of those hydrogens, and I'm going to have the hydroxide left. So, like, if you want an overshadowing idea, like just a guess as to why that happens, it's really hard to get that other hydrogen off of there, all right? That's not a great reason, but that's an okay qualitative reason. We've got a numerical reason here in a minute, but again, key idea. Here we had hydrogen ions, here we don't, all right? So here the anion from the acid remained a spectator. Here the hydroxide actually acts as part of that reaction in that case. So let's take a look at the half reactions that go with this, and we can predict, like, would this have happened if we didn't have these numbers? Or rather, if we didn't have the activity series qualitatively, would this have happened qualitatively? And what's the other reaction? So I'm going to slide this aside for now. We're going to look at our individual half reactions, and if you're unsure about how those work, there's a video that I had about redox specifically, so feel free to brush up on those. In this case, I've got my oxidation half reaction. That is the zinc going to zinc 2 plus 2 electrons. And we'll pull some values for this in a minute. My reduction half reaction is the hydrogen ions. In fact, 2 of those plus 2 electrons going to elemental hydrogen. Okay. For the oxidation half reaction for our other equation here, we have the calcium turning into calcium ions. So Ca2 plus our 2 electrons. And for our reduction half reaction, we still have something going on, all right? But we need to take a little look right here to see what that something is. And I know this is probably very small on the camera, and that's fine, but this is our table of reduction potentials, and I've color-coded it to match with what we see on our activity series. In fact, if you would prefer, because of the way this is written, we can flip this upside down, and then the colors match a little better. These are all negative cell potentials, indicating that they're spontaneous in the reverse direction, in the oxidation direction, not in the reduction direction. So we're looking at this right here. And I want to line things up correctly. So this hydrogen lines up with this one, and that's 0 volts. Anything that is higher here is more reactive, and it can replace hydrogen ions in solution, all right? But take a look here. In the reaction we wrote right here, I didn't have hydrogen ions, I had water. So if I look here, not water, not water, not water, not water, not water. Oh, there, that's water, right? So what do I have present? Zinc and hydrogen ions. Zinc can oxidize, hydrogen ions can reduce. What do I have present? Calcium and water. Calcium can oxidize and water can reduce. 2H2O plus 2 electrons goes to H2 plus 2 OH minus. And as a quick guess right here, you can say to yourself, oh, anything in this direction from this equation right here, this yellow one with the water, should take place, right? And we can look at that numerically in a minute if we need to. So I'm going to move this stuff out of the way, and we're going to write that equation. We'll assign some cell potentials and see where things go from there. So I've got 2 waters plus 2 electrons, and that's going to give me my hydrogen gas and 2 hydroxides. All right, so I'm going to highlight right here, literally, the difference between these metal and acid and metal and water is the part where we have this half reaction versus this half reaction. We have reduction of hydrogen ions versus reduction of water, yeah, where we don't have those hydrogen ions. So that, in a nutshell, is what's going on. So if that's all you wanted to know, we can cut it off right there. We can do some quick electrochemistry calculations just for the fun of it that'll identify our spontaneity for these reactions, whether or not they take place quantitatively, all right? All right, so as we look at this one, we can pull our numbers off of the table. This is the oxidation direction. Here I've got zinc as a negative 0.76, so in the reverse direction it's going to be positive 0.76. That's volts. We're talking about half cell potentials, right? So we've got this one, and for the hydrogen reduction, that is based on our standard hydrogen electrode, which is in one of those electrochemistry videos, but that's 0.0 volts. And to get the overall cell potential from the two half reactions, you just have to add things up. Okay, so a little quick math here shows that's 0.76 volts for the E standard for our cell. All right, so these voltages are electromotive forces, right? And that's the E. And this can correspond to our Gibbs free energy, and that's how we can predict spontaneity. So what I want to note here is that our E standard for the cell is positive, right? Therefore, our Gibbs free energy is going to be positive, and the reaction is going to be spontaneous. Now, if you've never heard that expression before, you can go back to some of the thermodynamics videos, or you can just understand that spontaneous means it happens without outside intervention, all right? So spontaneous means it happens, all right? Non-spontaneous doesn't mean it doesn't happen. It means it happens in the reverse direction. And that's kind of confusing, but for right now, this is our way of saying it happens. In fact, if I can summarize that, positive number here, it happens. All right, let's get some numbers for this calcium and this water one. Again, we're just going to pull them off here. We play Where's Waldo to find calcium. And calcium is negative 2.76. I had to pause the video and steal that number from somewhere. Mysteriously, it's not on that cell potential table. But negative 2.76 in the reduction direction. Since we're oxidizing, it's a positive 2.76. And our standard cell potential for our water reaction is going to be negative 0.83 volts. So negative 0.83 volts. That's going to give us 1.93 volts for our difference there, which is also positive, which means we're expecting also spontaneous. The standard for that cell is 1.93 volts. And by that same reasoning from before, our standard cell potential is positive. Our delta G, our Gibbs free energy, oh boy, that was a mistake there, negative. Our delta G is negative, therefore the reaction is spontaneous. Right? It happens. And I want to take note there, whatever words I said a minute ago. This negative delta G corresponds to positive cell potential by the Nernst equation, delta G equals negative NFE. So if E is positive, then delta G is going to be negative. So bear in mind. So what we've got here, this is going to happen, this is going to happen. And let's glance at maybe one of these and see if we can find one that won't happen. And we can take a look at, I guess, maybe one of the acid ones first, and we'll see how that goes. All right, so let's say we have like gold and nitric acid, HNO3. We would predict no reaction. In fact, as you look here, here's gold, and it explicitly says doesn't dissolve in simple acids. You can mix gold and sulfuric acid or whatever, sorry, nitric acid and sulfuric or whatever, and make aqua regia, but that's a totally different scenario. Gold and nitric acid. We're expecting no reaction. Okay? But if we did have a reaction, it would be something like our gold plus hydrogen ions plus nitrate ions gives us our gold and some 3+, and our nitrate ions, and now in this case diatomic hydrogen, right? And in order to make that work out, I think we end up needing like a 6 and a 6 and a 3 and a 2 and a 3. Oops, this is a 6 here, sorry. And a 2. All right, 6 hydrogens, 6 hydrogens, 6 nitrates, 6 nitrates, 2 golds, 2 golds, and it doesn't look like we can reduce that. Had I just followed my table like I tell you to, we wouldn't have had that hiccup. All right, So as we look at that, we're expecting no reaction. That's what the activity series tells us. Let's look at the numbers and see how that actually works out. This is our spectator. I'm not even concerned about it. We're worried about our gold here, so our oxidation reaction is our gold. Going to gold 3+ with 3 electrons. We'll get a number for that in a minute. Our reduction half reaction is going to be the hydrogen ions, right? It's like this, so we're going to have those hydrogen ions, 2 of them plus 2 electrons going to hydrogen, okay? Our standard cell potential for that gold is right here. It's 1.40 volts to reduce it, so that's negative 1.40 volts to oxidize it, all right? Negative 1.40 volts. Then we know our E standard for the hydrogen reduction is 0.0 volts. And when we add these together, we get our E standard for the cell of negative 1.40 volts. And that's different, right? Because positive, positive, negative. And when your standard cell potential is negative, you're looking at a corresponding delta G value that is positive. And what that means is the reaction is non-spontaneous. And so, like, non-spontaneous doesn't mean no reaction will happen. It's a way of saying that if we had the products, they would turn into reactants, okay? So we're saying, given these two things, we can't make anything, right? But if we had these things, it would go that way. So spontaneous in the reverse direction. And the idea of reactions going in a reverse direction may be a little foreign if you haven't done equilibrium problems yet. All right, so looking for a highlighter here. How about pink? So as you look at this, we predicted no reaction, and we got no reaction because our delta G was 0. Qualitative from the activity series, quantitative from the electromotive series. Let's do one last one, and then we can wrap this up. We did our metal and acid, we did metal and water, we did metal and acid, and now let's do metal and water. And we'll just pick something maybe like copper. So we'll say copper and water. And it doesn't really matter, but we can put liquid in this case. If you look here, we'll not dissolve in simple acids and not even close to the stuff that'll react with water. So based on that, we're expecting no reaction, all right? But to pretend we will have a reaction, let's just say that we have our copper and the water, which I will call HOH, right? And that's going to give us copper hydroxide, copper 2 hydroxide, and hydrogen gas. If we put a 2 there, it's balanced. And so what is going on? Well, copper oxidation is one of our reactions there. And our reduction half reaction is not hydrogen ions, right? Like here we saw hydrogen ions. Here I have water, so we have a totally different reduction equation, right? We've got the 2H2O plus 2 electrons giving us hydrogen and 2 hydroxide ions, all right? We've got one of these values. We'll grab the other one from our electromotive series in a second here. E standard on that one, negative 0.83 volts. E standard on this one for copper, 2+, is right here at a positive 0.3 volts for reduction. So negative 0.3 volts, 34 volts for oxidation, negative 0.34 volts for oxidation. So we're going to add these together, and it looks like we get like a negative 1.27 volts or something like that. Negative 1.27 volts as our E standard for the cell. And I'm going to write these same words, right? Since the E standard for the cell is negative, we're expecting our delta G to be positive, therefore it's going to be non-spontaneous. Right? And for simple street terms, you could say it's not going to happen, right? But if we look here, I've got no reaction predicted, and I've got no reaction predicted because this is a negative. All right, one thing that I want to mention with these half-cell calculations is that we did not take into consideration the actual half-reaction balancing. This one would have been okay because the electrons match. In fact, this one would have been okay because the electrons match. But if you look here and here, if you consider redox balancing, that's a 3 and that's a 2. And so we've got like 2s and 6s and 3s over here. They don't come into play when you're calculating cell potential, all right? So that's something we'll talk about more in an electrochemistry video. But right now, I do want to say, this is a 3, this is a 2, but we're not taking stoichiometry into consideration for generating these cell potentials, right? This is supplying electrons. This other reaction is using electrons. And just a minor note here relating to the words that say like react vigorously with cold water, react with steam. And I added in, the internet has told me that these two are likely to react with hot water. And the short of it is, the farther this way from our half reaction right there, the more favorable it is, and the less energy, the less energy it's going to take to initiate that reaction, maybe an activation energy. So this lithium is very likely to react with water, right? As you get down to the iron, we actually flip over to the other side here of our reaction. And so you wouldn't expect it to happen, right? You've got a positive 0.44 when we flip that and a negative 0.83, a difference of 0.39, and it's negative. So it seems like we have to increase the temperature to nudge that reaction into the spontaneous direction. Just a little side note there about being close to this reaction, and this half reaction, and being able to adjust the spontaneity using some temperature changes. And that's a big topic in thermodynamics, is at what temperature will some reaction be spontaneous. All right, once again, slow-mo. What do we have? What can it do? Metals and acids. We've got hydrogen ions, and they can be reduced. And metals and water, what do we have? We have water. And it can be reduced by a different process, right? So it is this reaction and this reaction versus this reaction and this reaction. All right, end of single replacement.